Section: Introduction. In this section, we discuss recent findings in large language model (LLM) reasoning that suggest we can enhance reasoning abilities by increasing the computational resources used during testing. Typically, these methods train models to generate longer reasoning sequences than the usual correct answers, using tokens that mimic some form of algorithm, such as reflecting on past answers or planning. These methods involve fine-tuning pre-trained LLMs for algorithmic tasks or applying reinforcement learning with a binary correctness reward. While training models to generate lengthy reasoning chains has shown promise, we need to address some key questions to continue improving the use of computational resources. First, do current LLMs effectively utilize the computational resources during testing? Specifically, do they use a reasonable number of tokens compared to the typical solution length, or do they overuse tokens even for simple questions? Second, can LLMs find solutions to more complex questions when given a larger number of tokens than they were trained with? Our goal is to ensure that every token produced is useful, which is essential for efficiently solving more challenging problems. We frame these challenges in the context of meta-reinforcement learning. Our approach involves breaking down the output from an LLM into multiple episodes. If we focus solely on efficiency, the LLM should learn to quickly provide the final answer without unnecessary episodes. Conversely, if the focus is on discovery, the LLM should explore various strategies over several episodes before arriving at the final answer. This differs from traditional reinforcement learning, as we aim to teach the LLM to balance exploration and exploitation for each problem. From the literature on meta-reinforcement learning, we understand that effectively balancing these two aspects is akin to minimizing cumulative regret, which measures the difference in success likelihood between the LLM and an ideal model. By training the LLM to minimize this regret for each query, we develop a strategy that is adaptable to different testing budgets, allowing the LLM to use only the necessary tokens while still progressing with larger budgets. We introduce a new fine-tuning method called Meta-Reinforcement Fine-Tuning (MRT) that minimizes cumulative regret, providing a way to evaluate existing reasoning models. Our findings indicate that state-of-the-art LLMs fine-tuned with outcome-reward reinforcement learning do not improve their chances of finding correct answers with more episodes, which is crucial for tackling difficult unseen problems. Interestingly, a simpler method of using fewer episodes with majority voting often performs better on challenging questions. We demonstrate that optimizing for progress, alongside outcome rewards, naturally arises when minimizing regret. Our MRT approach includes a reward bonus for reinforcement learning that measures the likelihood of arriving at a correct answer before and after each episode. We evaluate MRT in two different settings. In the first, we fine-tune various models on math reasoning problems and find that MRT consistently outperforms outcome-reward reinforcement learning, achieving state-of-the-art results with significant improvements in accuracy and token efficiency. In the second setting, we fine-tune Llama 3.1 models to implement backtracking, where MRT also shows notable improvements in token efficiency. We analyze MRT and find that it achieves lower cumulative regret and maintains steady progress, even when tested with larger token budgets than it was trained on. Unlike other methods that limit output length at the expense of accuracy, MRT reduces output length while enhancing accuracy. We also observe that output length can vary during reinforcement learning, and length alone does not guarantee accuracy. Lastly, we highlight that strategies for gradually increasing testing budgets tend to maximize progress and minimize regret more effectively than training with a large output budget from the start. Section Summary. In this section, we explore how optimizing test time compute through a meta-reinforcement learning approach can enhance the reasoning capabilities of large language models, LLMs. We introduce our meta-reinforcement fine-tuning, MRT, method, which minimizes cumulative regret to balance exploration and exploitation, leading to improved accuracy and token efficiency compared to traditional outcome-reward reinforcement learning methods. Section: Related work. In this section, we discuss how earlier research has scaled test time computation by training separate verifiers for methods like best of n or beam search, which can be more efficient than simply increasing data or model size. Building on this, recent studies have trained large language models, LLMs, to mimic in-context test time search by fine-tuning on search traces. However, we find that the benefits of these methods are limited because fine-tuning on unfamiliar search traces can lead to memorization. To address this, we implement a warm start procedure before applying on policy star RL. We also explore reasoning with long chains of thought, COT. Reinforcement learning, RL, with outcome rewards has shown potential for fine-tuning LLMs to generate long COTs that can search, plan, reflect, and correct. Some recent works have introduced length penalties in the reward system to manage the length of outputs based on problem difficulty. However, we note that length does not always correlate with accuracy, and many long COT models use excessive tokens. We attribute this inefficiency to the limitations of outcome reward RL in producing solutions that make consistent progress. Similar to our approach, other studies also utilize dense rewards, but the design in MRT is based on regret minimization and does not require an LLM judge. While there have been attempts to distill traces from existing reasoning models through supervised fine-tuning, these efforts are separate from our focus on enhancing RL directly. Additionally, recent findings indicate that RL-trained policies perform better in scaling test time computation compared to supervised fine-tuning. We frame the optimization of test time computation as a meta-RL problem. A recent survey suggests that how to think with meta-chain of thought is a promising avenue for advancing reasoning models. Previous RL research indicates that solving a meta-RL problem is essential for generalizing to new contexts with minimal interaction. Most meta-RL approaches vary in their adaptation procedures. Our method, MRT, is similar to meta-RL techniques that utilize in-context histories but differs in reward design, balancing between exploration and exploitation. Next, we outline our problem setup. Our aim is to optimize LLMs for effectively using test time computation to solve challenging problems. We assume access to a reward function that we can query on any output stream of tokens. For instance, for a math problem, the reward function can determine if the output is correct. We have a training dataset consisting of problems and their corresponding correct solution traces. Our objective is to train an LLM, modeled as an RL policy, to generate a token stream that maximizes the reward on test problems. In meta-RL, we train a policy to maximize the reward across a variety of tasks with different reward functions. The goal is to prepare the policy to perform well on unseen tasks. Instead of evaluating the policy based on zero-shot performance, we allow it to adapt through adaptation episodes during testing. Most meta-RL methods differ in how they design this adaptation process. Finally, we will formalize the problem of optimizing test time computation as a meta-RL challenge and demonstrate how this perspective can assess whether state-of-the-art models are effectively utilizing test time computation. We will also introduce our fine-tuning approach, MRT, aimed at optimizing test time computation. Section Summary. In this section, we discuss how previous approaches to scaling test time compute, such as training separate verifiers and fine-tuning LLMs on search traces, have limitations due to memorization and inefficiencies in reasoning. We propose a meta-reinforcement learning (RL) framework to optimize test time compute, allowing LLMs to adaptively tackle new problems while effectively utilizing rewards to improve performance. Section: Optimizing test time compute. In this section, we focus on optimizing the performance of a large language model, LLM, during testing while adhering to a compute budget. Our goal is to maximize the model's performance on the test set within a specified budget, which is typically larger than what is needed for a correct response. This allows the LLM to use some of its token budget for operations that may not directly solve the problem but help in finding the correct answer. For instance, in a math proof question, if the model can recognize that it needs to backtrack and try again, it can improve its chances of success and learn which steps to avoid. However, the compute budget for testing does not always match the budget used during training. Training the LLM to achieve high rewards with a fixed token budget can lead to inefficiencies, especially when the expected solution length is much shorter than the training budget. This can result in the model being unable to complete its response if deployed with a smaller budget. To address this, we propose a budget-agnostic strategy that allows the LLM to adapt its behavior for various budgets. This strategy encourages a balance between exploring different approaches and exploiting known strategies to make the best use of the available compute. We aim to characterize how budget-agnostic LLMs can optimally use their compute during testing. We can do this by breaking down the output into meaningful segments, or episodes, which we can view as an adaptation process for the test problem. Each episode can consist of multiple attempts, alternating between verifying and generating responses, with the goal of improving performance over time. Since the LLM does not know the testing budget, it must consistently make progress by balancing exploration, like verifying previous steps or trying new strategies, and exploitation, building on a chosen approach. We see this adaptation as a reinforcement learning (RL) process, where earlier episodes provide context for the current problem-solving efforts. We define an optimal algorithm as one that steadily progresses toward a solution with each episode, balancing discovery and exploitation. We can measure the effectiveness of this process using the concept of cumulative regret from RL. This regret indicates whether the episodes are making meaningful progress. A high regret suggests little progress, while a lower growth rate in regret indicates that the LLM is effectively utilizing its budget as it grows. Section Summary. In this section, we explore how to optimize test time compute for large language models, LLMs, by allowing them to balance exploration and exploitation within a flexible token budget, rather than committing to a fixed budget. We propose a budget-agnostic training approach that encourages LLMs to adaptively segment their output into meaningful episodes, facilitating a more effective problem-solving process that can improve performance across varying test time budgets. Section. Case Study. Analyzing SOTA DeepSeek R1. In this section, we analyze state-of-the-art models, specifically the DeepSeek R1 family, using the concept of cumulative regret. Although we do not have the ideal Oracle comparator, we can still evaluate performance based on different numbers of episodes in the thought process. This helps us understand if cumulative regret increases slowly over time. We focus on the DeepSeek R1 Distill Qwen 32B model, testing it on two datasets, AMI 2024 and a subset from OmniMath. An episode is defined as a continuous segment of the model's thought, marked by the tags "less than think greater than" and "less than think greater than", and is interrupted by words like "wait" or "alternatively". We measure our results using the major at P metric, where we truncate the thought block to the first J episodes and prompt the model to produce a final answer based on this truncated block. We then sample these immediate answers multiple times and use a majority vote to get a single response. We discovered that to end the model's thinking process early, we need to prompt it to formulate a final answer based on what it already has. By observing how the major at P metric changes with J, we can see if adding more episodes helps the model progress and find the correct solution. We compare this to a direct baseline, where we fine-tune the base model to give best guess responses. In our analysis, we plot the average accuracy of the model at different episode counts as a function of test time compute and the episode index. We average across solutions with similar episode counts to show the relationship between improvement and total episodes. The direct baseline is shown in orange, while the major at 1 metric is in blue. The dashed green lines extend the average accuracy at the end of each episode to the major at P metric for different numbers of solutions. Our findings indicate that with a few episodes, cumulative regret is low, and each new episode reduces regret. However, in scenarios requiring more episodes, we see that accuracy does not consistently improve and can even decline with additional episodes. This suggests that current training does not effectively optimize regret, even though it is possible to minimize regret using information from intermediate episodes. Surprisingly, longer traces with multiple episodes should be able to implement the major at P baseline without needing new knowledge. Yet, reasoning with sequential episodes does not outperform both baselines when more episodes are involved. This inconsistent progress with additional episodes indicates poor performance as we increase test time compute. If outcome-reward reinforcement learning were effectively enhancing the model's scalability, we would expect consistent improvements. Section Summary. In this section, we analyze the performance of the DeepSeek R1 Distill-Quen 32B model using cumulative regret metrics across different episode counts on 2 datasets. Our findings reveal that while initial episodes reduce cumulative regret, performance degrades with more episodes, indicating that current training methods do not effectively optimize regret as expected. Section. The Meta-Reinforcement Fine-Tuning (MRT) Paradigm. In this section, we develop a fine-tuning approach called Meta-Reinforcement Fine-Tuning (MRT), which aims to create a budget-agnostic large language model (LLM) that consistently improves. MRT fine-tunes LLMs to optimize a measure related to cumulative regret. Simply focusing on maximizing rewards over time does not effectively minimize regret during testing. If the LLM eventually succeeds in some way, all previous attempts are reinforced equally, ignoring their individual contributions to that success. This presents 2 main issues. First, we might exhaust our token budget without making progress on difficult problems, and second, we could waste tokens on simpler problems that could be solved more efficiently. To tackle these issues, we propose optimizing for cumulative regret, but we face a challenge because we do not have access to the optimal comparator policy. This lack of access is not surprising, as even during the training of any reinforcement learning (RL) algorithm, we cannot access the comparator policy for minimizing cumulative regret. Here, we measure cumulative regret not during training steps but based on the token output during testing for a specific query. Consequently, we introduce a surrogate objective that trains the LLM to adopt a strategy that minimizes regret when deployed. This approach helps balance the use of tokens for exploration, trying new methods and verifying previous answers, and exploitation, committing to a simplified expression based on a plan. Since we cannot directly optimize regret due to the unknown optimal comparator, our main idea is to minimize cumulative regret by maximizing the progress of our policy as more episodes are generated. We can illustrate this with a multi-armed bandit problem, where we need to find the best option while balancing 2 behaviors, exploring new but risky options and exploiting the best known option. Each action should ideally lead to an improvement in our understanding of the best option based on previous episodes. We build a simple surrogate objective where the episodes are like pulls, in our bandit analogy, and our meta-prover policy aims to estimate the best option. We expect to see minimized regret as long as the meta-prover makes progress, meaning that the measure of progress increases with more episodes. Importantly, this does not require each episode to provide a better solution but should increase the likelihood of arriving at the correct answer. Next, we define a standard fine-tuning loss function based on the expected final reward from the last episode. We can train the LLM using policy gradients or supervised fine-tuning on self-generated data. We extend our objective to include progress, introducing a reward bonus based on previous contexts. The meta-prover policy can be another LLM or the same LLM after its reasoning has concluded. Using the previous policy helps ensure we improve upon it and allows MRT to be implemented conveniently without needing complex rollouts. We can provide additional rewards either for specific episodes or as a cumulative bonus at the end of the reasoning process, with different methods affecting the variance of the gradient update. Unlike traditional RL that focuses on outcome rewards, MRT aligns with Meta-RL by evaluating progress across entire reasoning episodes rather than individual actions. While our objective may seem similar to others, we emphasize that progress is assessed across episodes, not just within a single attempt. With this framework established, we will outline specific implementations for supervised fine-tuning and reinforcement learning. Section Summary. In this section, we introduce the Meta Reinforcement Fine-Tuning (MRT) paradigm, which aims to optimize a budget-agnostic large language model (LLM) by minimizing cumulative regret during test time outputs rather than just focusing on final rewards. We propose a surrogate objective that encourages the LLM to make consistent progress across episodes, balancing exploration and exploitation to enhance overall performance. Section: Practical Instantiations, Dense Rewards for Optimizing Test Time Compute. In this section, we instantiate MRT to train a large language model, LLM, so it can effectively and efficiently utilize test time compute. We define each episode as a logical thought block marked by less than think greater than tags, similar to the DeepSeek R1 model. This approach is termed open-ended parameterization because it allows flexibility in the content of each episode. We optimize our objective using STAR and reinforcement learning, RL. With STAR, we sample on policy traces and clone those that not only succeed based on outcome rewards but also show significant progress. In RL, we add a reward bonus that reflects this progress, either explicitly or implicitly. We also explore a backtracking search parameterization, where the model alternates between trying complete solutions and backtracking. We provide details and results for this approach in the appendix, focusing on one evaluation in the main section. We develop two variants of MRT that use on-policy rollouts to enhance test time compute by maximizing dense rewards based on progress. The first variant employs STAR, while the second utilizes RL. The STAR variant generates self-created rollouts from the base model to form a high-quality dataset for supervised fine-tuning, SFT. For each input prompt, we sample an initial trace within the less than think greater than tags and break it down into episodes. The meta-prover policy is designed to end the thought block with a "time is up" prompt, compelling the model to provide a solution. We calculate progress based on this policy and filter episodes that meet two criteria: they achieve maximum progress and ultimately succeed. We then run SFT on these selected traces and repeat the process multiple times. The RL variant of MRT follows a similar progress concept using online RL methods. For each episode, we compute rewards for thought prefixes using the meta-prover. The model samples several on-policy rollouts based on this prefix, balancing between continuing reasoning and stopping to provide a solution. During training, we optimize a reward that reflects progress rather than just a binary outcome. We prefer this approach for its compatibility with existing RL implementations. Next, we evaluate MRT's effectiveness in optimizing test time compute, focusing on achieving high accuracy while being compute efficient. We present our main results, compare MRT's efficiency with previous methods, and conduct ablation experiments to explore the relationship between token budget and progress. For our experimental setup, we fine-tune base models capable of producing traces with less than think greater than markers using MRT. For the STAR variant, we used two models, DeepSeek R1 Distill Qwen 7b and DeepSeek R1 Distill Qwen 1.5b, fine-tuning them on 10,000 randomly selected problem solution pairs from Numina Math. We estimate the progress bonus for backtracking by rolling out each prefix multiple times. We compare MRT, which includes progress as a bonus, with vanilla STAR that relies solely on outcome rewards. For the RL variant, we used DeepSeek R1 Distill Qwen 1.5b and DeepSeek ALER 1.5b preview, comparing MRT with outcome reward RL. We fine-tuned DeepSeek R1 Distill Qwen 1.5b on 4,000 Numina Math problems, while DeepSeek ALER 1.5b preview, which had previously undergone outcome reward RL fine-tuning, was fine-tuned on 919 AMY problems from 1989 to 2023. We also compared MRT to an RL method that penalizes token length, with an average response length of around 8,000 tokens. We set a maximum token budget of 16,000 for fine-tuning and evaluation. More details and hyperparameters are available in the appendix. Section Summary. In this section, we instantiate the MRT framework to train a large language model, LLM, for effective test time compute by utilizing two variants, one based on STAR and the other on reinforcement learning, RL, both optimizing for dense rewards linked to progress. We evaluate the efficacy of MRT against prior methods, focusing on achieving high accuracy while maintaining compute efficiency, using various base models and problem sets. Section: Results for MRT. In this section, we report the pass at 1 performance of outcome reward reinforcement learning, RL, and MRT across several math reasoning datasets, including AMY 2025, AMY 2024, AMC 2023, Minerva Math, and MATH 500. We used 20 samples per problem to minimize noise from the limited dataset size. Our findings indicate that MRT performs better than training on the same dataset without the dense reward bonus. We have made several noteworthy observations. 1. State-of-the-art results. Our models, fine-tuned from the DEEP SCALER 1.5B preview base model, achieve top performance for their size. Although the absolute performance gains are modest since we build on already trained models, the relative improvement from using MRT is about 2 to 3 times greater than that from outcome reward RL. 2. Better out-of-distribution robustness. When fine-tuned on a narrow dataset of AMY problems, MRT not only performs better on AMY 2024 and AMY 2025 but also maintains its performance on the AMC 2023 dataset, which is somewhat different from the training data. 3. Larger gains with weaker models and broader training data. The performance improvements are even more pronounced with the DeepSeek R1 Distill Qwen 1.5B model, which has not been trained with RL, compared to the already RL-trained DeepScale R model. We also tested an explicit length penalty on the DEEP SCALER 1.5B model to enhance token efficiency, but this resulted in lower pass at 1 accuracies, aligning with findings from concurrent research. Next, we evaluated whether MRT, RL, enhances token efficiency in solving problems. We trained the model with a 16K context window and calculated MAJ at K across various reasoning and solution traces. Our results show that MRT outperforms the base model by an average of 5% accuracy for the same token count on AMY 2024. Additionally, MRT, RL, uses 5 times fewer tokens on AMY 2024 and about 4 times fewer on Math 500 to achieve equivalent performance compared to the base model. Overall, MRT improves token efficiency by 1.2 to 1.6 times over outcome reward RL, demonstrating significant gains while maintaining or enhancing accuracy. We also trained 7 B base models with MRT, STAR, and these results are detailed in the appendix. In the backtracking search setting, we constrained the model to produce a solution, followed by error detection and revision. We trained with Llama -3.1-8B and 3B base models, using 20,000 randomly sampled question solution pairs from the Numina Math dataset. Our evaluation utilized AMY problems from 1989 to 2023, where LLAMA 3.18B achieved a pass at 1.0 of about 30%, significantly lower than the 60% on the Numina Math training set. We compared MRT, STAR, to outcome reward RL and RISE, a self-correction method that does not use backtracking. For evaluation, we assessed MRT in 2 modes: parallel mode, where we sampled independent traces per problem, and linearized mode, which allowed for longer, coherent outputs by retaining the last 2048 tokens. This sliding window evaluation was not feasible for open-ended parameterization but was possible here due to the structured episodes. When evaluating the STAR variant of MRT with the LLAMA 3.1-8B model, we found that MRT achieved the highest efficiency in both evaluation modes, improving efficiency by over 30% in linearized mode. While RISE also improved performance, it did so less efficiently than MRT. Finally, We assessed the RL variant of MRT on top of GRPO with a 3B model after WarmStart SFT. Our results show that MRT, RL, enhances linearized efficiency by reducing token usage by 1.6 times compared to outcome reward GRPO. Section Summary. In this section, we demonstrate that MRT significantly enhances performance on various math reasoning datasets, achieving state-of-the-art results and improving token efficiency by requiring up to 5 times fewer tokens to reach comparable accuracy. Additionally, MRT shows better out-of-distribution robustness and greater performance gains when applied to weaker models and broader training data. Section: Ablation Studies and Diagnostic Experiments. In this section, we conduct controlled experiments to gain insights into why MRT is effective. We seek to answer two main questions. First, do MRT with reinforcement learning and MRT with STAR lead to less cumulative regret and greater progress compared to traditional outcome reward reinforcement learning and STAR? Second, what is the connection between token length and progress, and how does this length change during MRT with reinforcement learning? We will present some ablation experiments to address these questions.